Thank you for the introduction and thank you for the invitation. Okay. So in my talks, I try to describe some of the geometry domains in Cn. Okay. So I usually assume this is strictly pseudo convex. I give a definition later. And if you have a domain, the boundary is called CR manifold. So my notation is a little bit different from the one with ML. ML use B, but I prefer to use partial. This is a boundary for me. Okay. Other part is almost same. Domains omega, dimension is n. So in many people in CR geometry prefer to use n plus 1. So this talk, n is the dimension. So, okay. So let me start with the simplest case. It is trivial for my consideration. So n equals 1. So this is not several complex variable. It's classical. Look at the domain in C1. Suppose that this is, say, bounded. Simply connected. Simply connected means there's no hole. So omega is a domain. So this is a one dimension, complex dimension. So I can draw a picture. So there's no hole, so I don't draw a hole. So this is omega. So simplest example is a disk given by this definition. See the problem, can you find a holomorphic map which sends this to this? And the inverse is also holomorphic. So this is solved by Riemann. This is called Riemann's mapping theorem. It says, under this assumption exists holomorphic, and the inverse exists and holomorphic. So I call this is a biholomorphic. So if domain has no hole and bounded or not equal to the C itself, it is biholomorphic. So if you consider biholomorphic geometry of simply connected domain, that's the end of the story. This is the model and there's no other choice. So this is very simple. And moreover, if boundary is smooth, then F extend to C infinity diffeomorphism from omega closure to the disk closure. So the correspondence of boundaries are also very nice. You can really, so the boundary behavior is very smooth if the boundary itself is smooth. Okay, so we want to consider the higher dimension. Okay. Then the model case is the ball. So Z in Cn, Z2 square, Zn square equals. So I use the notation for this norm. Okay, this is a ball. I draw the same picture, but this is ball for me. Okay. The fact is that many domains near omega 0 are not pick each other. So near means just part of a little bit bump. Consider domain like this. So there are many ways to make such a deformation. Then almost always they are not biholomorphic. So they're like infinite dimensional family of such inequivalencies. So we say moduli of biholomorphic domains are infinite dimension. So we want to understand the geometric structure of this moduli. So that's a final goal. So just recall the definition. So domain in Cn. So F omega is biholomorphic. This means F. So we have components of this map, and so all F, J, Z are holomorphic, and F inverse is also holomorphic. Okay. So in one dimension, you can just say the F is homomorphic and the inverse is homomorphic. In this case, so you have more components. So holomorphic map between Cn to Cn is just each component is holomorphic, and the inverse has components which are holomorphic. So this is the definition. So we want to classify domains by this equivalence. Here's an example. So this is called due to Webster normal form for ellipsoid. So consider domain with parameter a to an given by the equation Z in Cn. So plus it's a little bit small perturbation of the ball. So this is the norm defined there. So I add AJGJ square plus GJ square. Okay, here, let me note this vector by A, and I assume that this is real So you can assume that this is positive, because if it is negative, you can change variable easily, and then it should be bounded by half. It's not allowed. So it will be bounded domain if this is bounded by half. Okay, the statement is that so these are real ellipsoid. Two domains are bihomorphic. If and only if A equals A prime. Okay. So this is a complete classification of real ellipsoid. So real ellipsoid is a real composite. So you consider 2n, so Cn equals Rn, and then you can use real variable and quadratic form less than 1 define ellipsoid. And if you choose good complex linear transformation, any ellipsoid centered at 0 can be transformed into this form. This is not so difficult. It's just a linear algebra. Then, for such ellipsoid, the bihomologic map exists if and only if these numbers exactly equal. The proof is not easy. So Webster used reflection principle in higher dimensions and show that any map, bihomologic map between this to this should be complex linear. Then you can classify it. But that part is not easy. So I don't go into the detail about this, but this tells you there's at least n-dimensional inequivalent classes. So if Aj is small, this is very close to the ball. So just changing a little, it doesn't change C-infinity structure or topology of the domain, but it is defined as a bihomologic geometry. Okay. Other example. This is more classical and easy. So when you want to say two domains are not bihomologic equivalent, the one strategy is to make an invariant. If the invariant is different, the domain should not be equivalent. So one way to construct that is take automorphism group. So this is a F from omega to omega bihomorphic. Okay. So consider, so this is a map from domains to groups. So take domain, then automorphism groups. So you can assign each domain a group. If two domains are bihomorphic map from both, then it should be true that isomorphism as a group. This is trivial fact because you can compose this F with a bihomorphic map. You can prove back all the such F to on omega prime to omega, and that should be the isomorphism of the automorphism group. So by this observation, if you can find two domains which has different automorphism group, that should not be equivalent. So Poincore or maybe Reinhardt say that if take omega 0 in C2 and polydisk in C2, then take aught compute this. It's not difficult. I will do this later, and this is just a product of the automorphism of disk and the permutation. So it's rather both easy, but this is not isomorphic. So omega 0 is not bihomorphic. Okay, so this is maybe the first example for the domains which are not bihomorphic. So this is a starting point of the bihomorphic geometry. Maybe it goes back more than 100 years. But after that, there are many detailed study, and this should be the 1980s. Webster gave such a simple example, and geometry, that's the end. Okay. requires more tools and more method to construct invariants. Okay. So we assume one more comment. So it looks like this is a good strategy, but this is not so helpful when you consider just a perturbation of this ball. So for this case, automorphism almost always just identity. So there's no information. So there's some automorphism only when some of the numbers are equal. So there's an equality, you have something, but otherwise, or if you have a zero somewhere, then you have automorphism. Otherwise, this is just a discrete group and not much help. And also, if you perturb for almost all domain, automorphism is just identity. So from the point of view of differential geometry, that's not so helpful. Okay, we assume that omega is strictly pseudo-convex. So let me S psi C for short. So MAOs already gave a definition of pseudo-convexity. Strictly pseudo-convexity is just changing the E. Okay, let me write down. So suppose omega is given by low, I don't like. So the positive inside, this may be different from the. Then Zj, Gk bar, rho. Jk equals 1 to n wj wk bar. So for people doing analysis, use defining function which is negative inside. So this is because you don't have to put minus here, but I'm a geometer, so geometer prefer, or later I want to take a log of law, so I want to make it positive. So I have to take a positive defining function, so I put minus here. This should be positive for any w set not zero, such that 1 to n wj zj equals 0. So complex tangent vector to the boundary at point P, any P in boundary. Okay, this is at P. So there's no equality here. So that's me, strict pseudo-convex. So of course, it's natural to consider pseudo-convex domain and do bihomologic geometry. That is very difficult. So it's like doing Riemannian geometry for which metric degenerates some points. So then you cannot define curvature, no connection, and the model case is not homogeneous, and all the tools in differential geometry just break down. So I need to assume strictly pseudo-convex to do some differential geometry. It is still very difficult. Okay. So this is the definition. So the ball is strictly pseudo-convex. So small perturbation of the ball is also strictly pseudo-convex. You can just consider such an example. The problem already difficult enough for such a small perturbation. Okay. Let me Fetterman extension. So in the one-dimensional case, I stated that if the boundary is smooth, the Riemann's mapping can be smoothly extended to the boundary. So it's also for higher dimension if we assume that omega prime in Cn, C infinity boundary, and strictly pseudo convex, then maybe bound it always. I don't want to look at the infinity, so this is a bounded strictly pseudo convex domain. Suppose that there is a biholomorphic map. If F is biholomorphic, then it extends to C infinity diffeomorphism omega bar to omega prime bar. So I use the same notation for this extension. So we have a strictly pseudo convexity and smoothness. The biome map extends smoothly to the boundary. This is a very difficult theorem. So Fetterman has to do detailed analysis of the Bergman kernel and then do the analysis of the Bergman metric and its geodesic. So this is one reason he got the Fields Medal. So I don't want to prove this, but please believe this. This is the basic starting point for my shear geometry view. So you have a biome map. Inside, it extends, so you can talk about the boundary behavior. So, if you restrict this to the boundary to boundary is C infinity different. Okay, so you have a maps inside it extend to the boundary and the boundary corresponds nicely. Okay. Then what is the property of this boundary map? Then I have to introduce CR structure. This CR stands for Cauchy Riemann. So there's a Cauchy Riemann equality inside, and if you take the boundary value, it is called tangential Cauchy Riemann equality, and one geometric way to stating that equation is this CR structure. So CR structure of boundary is a subbundle of complexified tangent bundle. So usually tangent bundle is a real vector, so we consider complication. That means sum of, so if you have a vector field V and U, just a tangent vector, this is a real tangent vector. So alpha B plus complex vector means B plus root more. Some formal expression. This is just this space. Linear combination of real vector by putting I here. Okay. We already used this such a things here. So this W is considered a complex vector. Okay, all bundles given by so take P on the boundary at the point P, 1, 0, partial omega equals z equals aj gj n. This is in T10 Cn at P. So if you don't know this notation, T10 of Cn, this is just a space or vector of this form, differential operator of this form. This is a Cauchy Riemann operator times complex numbers. The sum, linear combination of the thing is, I will prefer this big Z. Okay, Z, such that Z applied to rho at P equals 0. So this is the same as this. Okay, this is the defining equation for this tangent, complex tangent bundle of the boundary. So this, if you go back here, this just say Wj, Zj, sigma j equals 1 to n, T1, 0 of the boundary at P. Okay. So I'm using bundle notation here instead of the explicit equation. So this is a bundle. And rho is a defining function. Also, I should say rho is positive. Define omega, and the gradient is not 0 on the boundary. So this is the definition of defining function. So there are many choices of a defining function, but this equality is same for any choice. If you use some factor here, just comes out. So tangent to the boundary is the same. So this is a subbundle, and small f is a CR map. This is a definition. If push forward of this T10 boundary is contained in T10 of the target. So this is again complexify the push forward. So this is a Jacobian matrix multiplication. So you can complexify it. Then this subbundle is preserved by this map. This is a CR map. You can compare this with the fact that compare omega to omega prime is holomorphic if and only if push forward using big F P10 omega, then that should contain in omega prime. Okay. So this is a bundle of AJ, GJ. No restriction, just linear combination of holomorphic Cauchy Riemann operator, these functions. So this bundle should be preserved by the push forward. So this is equivalent to the Diva equation, and homomorphicity can be rephrased as a preservation of the bundle. Okay. So this is just a restriction to the boundary of this equation. So if e.g. fact, so corollary of Fetterman's result. Tell me that if F by holomorphic, Then the boundary is CR. So CR map and also the inverse is CR. So then I call it CR isomorphism. So CR isomorphism means F and F inverse are CR map. Maybe I can say by CR map, but people doesn't use that word. So CR isomorphism. So if the inside the bihomorphic boundary is CR isomorphic, the natural question is what's happened. If the boundary is CR isomorphic, can you extend this to the homomorphic map inside? That is rather easy. So this is called maybe CR version of Hartog's extension. So suppose omega prime in Cn bounded C infinity with C infinity boundary. If F isomorphic map. So this diffeomorphism that sends shear structure to the shear structure of the target. Then yeah, maybe needed. So this is a domain. Maybe needed. C infinity and connected. Yes, if we assume this is pseudo convex, that should be connected better. Okay, I don't have to answer. It's better to ask. But this has nothing to do with pseudo convexity. So, yeah, okay, connected and smooth boundary. So this should be connected. Shear map, then external bound map to omega prime. So this is you can solve Debraj equation to extend, but this is an easy version of Debraj equation. So Debraj equation for the forms with compact support, so you don't have to really look at the boundary. So the original Hartog's theorem says why this is Hartog's theorem. It doesn't look like Hartog's theorem. So I don't need this, but it's usual Hartog's theorem says if omega in Cn, so n. So n is always, so here, if n equals 1, there's no CR structure. CR structure is just 0, so this is trivial, so always assume this. Then k in omega compact and omega k connected. So then any f holomorphic, any holomorphic f from omega k to c extend to holomorphic map omega to c. So if you have a domain and there's a hole, this is k, this is omega, so you have a holomorphic map defined on this component, this connected component that can be extended to k. So you cannot have a compact hole with singularity here. So this is a usual Hartog's theorem. So this is some limiting version of this. So consider domain, and suppose k is very big. Say k is given by rho epsilon. So if I apply Hartog's theorem for this setting, small, homomorphic function on this small neighborhood extend to the inside. So take a limit as epsilon go to 0. Then this becomes thinner and thinner and then become boundary. But the boundary structure is preserved, and this CR structure isomorphism is preserved. So you can see this as a limiting case of Hartog's theorem, but actually proof is almost same. So first you have to extend f to some smooth function for which Debraj equation valid to some order, and then you can solve Debraj equation to make correction. So the proof is almost same. So let's say this CR version. Okay. So we have equivalence. To sum up,
can we extend that outside as well?
No, not in. Yeah, you cannot do that outside. It really depends on the eigenvalue of Levy form. If you have negative eigenvalue, then you have extension or something. Now we are assuming this is strictly pseudo convex. You can extend the inside only. Okay. So you have. So combining two theorems, two domains for in Cn, strictly pseudo convex, C infinity boundary.
So question. Going back to the connectedness.
Yeah.
So from your argument, certainly one sees an extension to a holomorphic map. But for that extension to be biholomorphic, then there's probably some more topology, some more topological constraint.
But this is CR isomorphism.
Yes, you start out with a CR isomorphism.
Yeah.
But if the domain itself has some non-trivial topology,
non-feasible topology. These are domains in Cn. So we start with a domain with connected boundary.
You can just apply backwards.
You
can just apply the same result to everything.
Yeah.
To see that,
Extension one side, extension the other direction. Yeah, it should be unique and Okay, thank you.
And does there exist any analog of this theorem in n equal to 1? I mean, there is some isomorphism on boundary, and then I can extend it.
Yeah.
But there we don't have the CR terminology, right?
CR topology.
N is equal to 1.
N equals 1. There's no CR structure.
So I
Yeah.
mean, does there exist some other theorem that says on boundary we can go inside something? Like
No, it's not easy. Yeah. So if you just consider simply connected case, the boundary is just a circle, and then there's no way to do something. If you have more holes, then you have to look at the harmonic measure. That's a global question, and this is local condition, and it's completely different. Yeah. I don't say one dimension is easy for the domains with hole. That's a Teichmüller space theory. It's the other direction of mathematics. Okay. So two domains, bihomorphic, if and only boundary, CR isomorphic. So we have two geometry nicely connected. So I always need n equal or less than 2, strictly pseudo convex with smooth boundary. Okay. So there are two geometry. This is a bihomorphic geometry. And this is shear geometry. So sometimes this is easier and sometimes this is easier. So we have to choose which one to use. So the difficulty in bihomorphic geometry is this domain is not compact. So you have to really look at the boundary. So then you have boundary term in Emily's talk. So you have to always look at the boundary contribution. But here, this is a compact manifold. There's no boundary. The boundary itself is compact, and there's no boundary of boundary. Of course, you can think of a boundary of boundary, but it's too complicated. There is some theory, hypersurface in shear manifold. That's another theory. Okay, it's not the topic of this talk. So in this case, how to construct invariant. In both cases. So I say Bergman kernel is useful here. If you have a Bergman kernel, you can define Bergman metric, kernel and metric. I will define this later and both of this. But the difficulty here is Bergman kernel itself is difficult to compute. So computing Bergman kernel itself be the object of the bihomorphic geometry. So we can use Monge-Ampère equation. Monge-Ampère equation to construct another metric that is Kähler-Einstein metric. So I have to say complex. So if you use complex Monge-Ampère equation, you can really construct solution to some order. Then you can use that to describe Bergman kernel and the geometry of inside. Also, it has a nice relation to the boundary. Okay, so in the shear case, the geometry goes back to L.A. Carlton. He used moving frame methods, and this define curvature of shear geometry. And also there's a Mozart's normal form. So shear geometry, geometry of the boundary. So I should not cross here. Okay. So there's some normal form for this surface. There's a nice coordinate which makes the boundary looks like the sphere. So that's called Mozart's normal form. This is also define curvature. This also give curvature. Both methods give curvature of the shear geometry. But it's not easy to connect this to Bergman Kernel Monge equation directly. So Fetterman define ambient metric. Theory. So there's a connection. So in my talks, I have no time to do this. This is a completely different differential geometry. Starts with big bundle and Lie groups and representation theory involved here. But instead, I use some explicit formula in this one. And the basic tool is Monge-Ampère equation. From here, I can describe Bergman kernel. From here, I can define ambient metric. And this also connected to describe Bergman kernel, so you can apply this to this. Okay, so this is a big picture of this bihomologic geometry and shear geometry, and I try to describe Monge-Ampère equation, ambient metric, Bergman kernel, and maybe Mozart's normal form, but omitting this important thing. So this is missing in my talk. So if you are interested, I recommend you reference. Pseudo convex domains in CN by Beers, Fetterman, Grossman. This is a Britain AEMS 83. So the title is exactly the object of my talks, and this is 1983. So it's based on the lectures given by Fetterman more than 30 years ago. And Beers and Grossman and many other take notes and make this into a 200-page lecture note. So it contains much of the details of this picture. So this is already 30 years old. So first 3 lectures will be contained in this lecture note. So last 2, I go beyond that. So the lecture note ends with section 10. So I can chapter 10. So I can say what will be in the chapter 11 and maybe 12. Okay. So the basic materials is contained in this lecture note, and this is free to download. Okay. Okay. So this is a plan of this my talks. So that says I start with Monge Ampère, but let me start with the easiest one. That's the Bergman Kernel. That's easy to define. So I have 10 minutes. So Bergman kernel is easy to define, but difficult to compute. So omega in Cn, n can be 1 in this case, bounded domain. Then omega, all omega with the holomorphic function. Okay. Then the Bergman space is defined by the holomorphic function intersection with L2 function. Okay. So this L2 is a usual L2 for the Riemann measure on Cn. So integrates just over this domain. It's bounded, so there are many. So polynomials are contained here, and this is contain many functions. Okay, then lemma 1. So we have k in omega compact. So L2 compact. So there exists a constant ck positive such that for any f in Bergman space, sup of fz over z in this compact set is bounded by L2. So this is a L2 norm. Omega f squared dv. Okay. So the sup norm is bounded by the L2 norm. The proof, I don't give a proof, but the hint is that if you take a ball, P R, so this is a Z in Cn with Z minus P equal, take a ball contained in omega. So this is the statement. So taking average of holomorphic function over ball should give ball PR should be the ball PR of F Z dV. So holomorphic function is harmonic, so the average should give the value at the center. So if you take a sup norm, take a so this can be bounded by C L2. So for maybe better to in two steps, but should be elementary. So if you take this, and this is an L1 norm, but this is a ball, so you can boundaries by constant times L2 norm, and then extend the range of integral, then it's become L2 norm for this omega or the Bergman space norm. So this C depends on the distance from the boundary to the compact set K. So R should be smaller than the length, so I don't. Okay, so skip the details. The point is that from this fact, we can say that A to omega is a closed subspace of L2 omega. So closed means, so this is Hilbert space. This is closed in Hilbert space. This is also Hilbert space. And other thing that this is separable. Separable means you have a countable system, complete normal system for this, or countable set of which are dense in this space. So this follows from lemma 1 easily. So you can take complete also normal system Fj. This is countable in A2 in the Bergman space. Then define Bergman kernel of omega by the sum Fjz Fjw conjugate. So this is called so this BZW converge uniformly on each compact set. So suppose Z and W are contained in some compact set, then it converges uniformly. This comes from the fact from this estimate. So L2 norm. So the sup norm is estimated by the L2 norm. So the L2 convergence dominates the sup norm convergence. That's a uniform convergence. So uniform convergence by uniform convergence, we can say that this is holomorphic in Z and holomorphic in W. So Z first ZW contained in C infinity omega times omega. This is for Z, this is for W, and holomorphic in Z and anti-holomorphic in W. So we take conjugate here. So this is not holomorphic, but anti-holomorphic. Also, this is independent of the choice of Fj. So take any complete orthonormal system. The sum is same. This can be checked by using other characterization of the Bergman kernel using some sup of L2 function, or it's a standard fact. Okay. So this ZW is called the Bergman kernel of omega. Okay. So this is the definition. Definition is simple. Okay, it's time. Okay, Okay, just one example. Yeah. Yeah, I have to. If you define something, you have to give the example. So, example. It's a ball. Then B Z W equals pi n. Zj Wj conjugate minus n minus 1. So in this case, you can actually compute the orthonormal basis. So Z alpha complete orthogonal system. Complete orthogonal system. It's normal, not normal, so you have to divide it by the norm. So gamma alpha, okay. So BZ W equals sigma alpha of norm this alpha squared. So for the case of ball, you can compute this norm by using beta function, and this is because of geometric series. So you can compute this. It's not difficult. Okay. Then natural question, what's the other example? But unfortunately, if you stay in the bounded strictly pseudo convex domain, this is the only example you can compute Bergman kernel explicitly. I'm really confident about this. So if you can compute the Bergman kernel, that should be equivalent to the ball. If you can find some example for which you can compute Bergman kernel and you can prove that the domain which is strictly pseudo convex not bihomogeneous to the ball, that's a big surprise. So the main question will be how you can approximately compute the Bergman kernel for general case. That's the starting point of this Monge-Ampère equation. And you have to do many things to write down Bergman kernel. Okay, let me stop here.